keep going. Let's go back to the slides that we're looking at. So before the break, we were looking at different types of regression methods with linear, binary, logistic, Poisson, Cox, and people gave examples, right? And one of the things that I wanted to quickly point out is that if you remember from physics class, right, they taught us this equation of a straight line. And this equation of the straight line is the basis for linear regression, right? And it's also the basis on which we understand and interpret the rest of the regression methods, okay? So the idea is that you have numbers on a scatter plot and you're trying to find the line of best fit. And this is the line of best fit. And this slope is the beta. The beta estimate that we are always interpreting is the slope, okay? And this is the intercept. So this is beta 1. And this intercept is beta 0, okay? And that's beta 0, okay? And that's what we are trying to implement. And if you look on this equation of the straight line, this is beta 0, this C, and this is beta 1. And we looked at that when we looked at linear regression, okay? We earlier talked about predictor, explanatory, independent variable. We talked about response or dependent, the slope, or which is also the slope is also the effect, and the intercept. Okay, all right. So we can take this example, or we can keep going and go talk about other things. All right, let's take this example. So you're interested in assessing, this is an example we've seen in class. You're interested in assessing whether there's a difference between the number of years spent in residency training and the number of hours usually worked per week. The assumption is that maybe if a person has spent more years in residency training, they might have more control over their time, or they might have more responsibility. That means that they're expected to work even longer hours. So it depends on what's happening in your setting. But the key thing to remember is that these two are continuous variables. So the number of years is measured maybe 0.5, 2.5, 0.6, that kind of thing. It's not measured in whole numbers. And number of hours too is a continuous variable in this setting, right? So you have a regression model that looks like this, okay? And the question that I really want to ask is, how do you interpret the beta estimates? So how do you interpret beta 0? Anyone want to tell us? How do you interpret beta 0? Anyone?
Hello, can I talk?
Beta 0 is the intercept.
The intercept.
Is the hours worked when the residency year is 0.
When the residency year is 0. Okay, very good. Babatunde, I think you wanted to speak up earlier. Can you tell us what beta 1 is?
I like you said, that's the intercept, and that's the number of hours for which a resident will work, even if the person starts on day 1.
Even if the person starts on day 1. Excellent. So when the residency years is 0. Don't go yet. Don't go yet. So that is beta 0. All right. So what is beta 1, Babatunde?
So the beta 1 there is the slope, that is the coefficient that determines, or let me say a factor that is multiplied by the number of residents, number of resident years.
Okay.
So that determines the hours work.
Okay, so but here's the thing. If you want to interpret it, okay, what would it be? As the number of residency years increases by 1, right?
Let someone else try it.
Okay, all right.
Sir, can I try?
Let's have somebody else. Sorry, so that we can have more people talk. I really like your enthusiasm. let's have somebody else attempt it from the class, and then if we don't have anybody else, then you give it a shot. Anyone else in the class wants to try?
Okay, let me try now.
Okay.
For every unit of resident years, we have the hours worked increased by a factor of 1.
You're getting very close. For every unit increase in residency years, the hours worked increases by beta 1. Okay?
Yes.
Every time the residency years increases by 1, the hours worked increases by beta 1. So even though the beta 1 is on this side of the table of the equation, it actually refers to, it's what is a factor that you multiplied by the hours worked, like you said earlier. So every time the residency years increases by 1. So if you compare the person, who was on the first day of residency day 1 or day 0, and compared to residency after 1 year, right? How much different is the number of hours they would work? And we looked at that here earlier, and we found that beta coefficient in this study was 0.97, right? That means that if on average, and you remember, like Lawal said, that that the constant is the number of hours worked on day 0. Okay, the constant is the number of hours worked on day 0, right? So that means that if a person was starting residency and the first week of their residency, they're going to be working 70 hours already. Okay, and so, but then if you go and ask them in a year's time, how many hours are they working on average, you will find that they will be working 70.062 plus 0.97. So this is about maybe 1. So they might be working 71 hours. This is the way to think about it. Okay. And if you go and talk to somebody else, who is in the second year, the increment over by 1 year is going to be another 0.97 hours. That's what that beta 1 coefficient means. All right. Okay, very good. So that's how we interpret. And then I want somebody else to interpret the p-value for us. The p-value here is 0.17. Anybody else who hasn't spoken today wants to take this super easy question? Anyone else? Anyone who hasn't spoken today? This is the easiest question of the day. Just going to go for it and blow it out of the park. Anyone? Anyone?
Yes, sorry, can you hear me?
I can hear you very well.
Yeah, this is Monday.
Okay.
Yes, I think I love the question too. Very easy, like you said. Let me just give it a shot.
Yeah.
Now, the p-value here is 0.171.
Yeah.
Which of course is greater than 0.05. Yeah. And as such, we will, since the value is greater than 0.05, there is no statistically significant relationship.
Yes, very good. There's no.
Otherwise, if it's less than 0.05, then we'll accept, yes, we'll accept the null hypothesis. As it is, we'll fail to, I think we'll fail to reject the null hypothesis.
Okay. Okay, don't go yet. Don't go yet. Don't go yet. Don't go yet.
Okay. Yeah.
So we fail to reject.
Yeah.
Okay. We never accept.
Oh, yeah.
Okay. The term accept, we don't use it. We either say reject the null hypothesis or fail to reject the null hypothesis. I mean, it's semantics, right? When you fail to reject, it's negative, negative, double negative. And so you're really kind of accepting, but that's not the term that we use in statistics. And the reason we don't use that term is because we are what we're doing is sort of estimating. We're not sure, right? We're never sure of what we're doing. We're just getting as close as possible to the truth. Okay. So every time we want to leave a little wiggle room, so that if it ends up being wrong, they might say, well, we're unsure. Okay.
Yeah, thanks.
All right. Yeah. Excellent. All right. So this is interpreting the linear regression. And the last couple of minutes we spent interpreting the continuous, when the predictor is a continuous variable, right? So I want somebody else to give us and tell us how you would interpret. And so let me give you an example. So first of all, before we go, I wanted to point out this. Every time that we've written the equation, we've written y. Like here, it's just written the variable. But the reason why I introduced this is just to let you know that this E sign, this is to tell you that this y is really on average. Okay? It's really on average. So it's not as if we're talking about the individual person or the individual patient. We're talking about the average of a population. That's the context in which we're doing all of these methods. Okay, something to always remember, that everything that we're doing here is on average, is not relating to a specific individual. And the reason why we are saying that is that it gives us pause. So for instance, in the context of prediction in, say, machine learning, this is what they do in machine learning, by the way. They use regression methods like linear regression, logistic regression, okay? And then they add up the beta 0 and the beta 1 multiplied by x, and they might have maybe 10 variables like that. So beta 1, beta 2, beta 3, beta 4, whatever. And, and they add all of that up to obtain this y, right? The average for y. Now, sometimes when you predict an outcome in machine learning, it doesn't happen the way you expect it to be. And the reason it doesn't happen the way you expect it to be is that the specific individual that you're dealing with might have another factor, which is often called the error term, right? That makes their results different from the average. And so that's why we have to be always cautious and humble, be humble with your results. Don't be like, oh, I have this data set, I have perfectly predicted the outcome, and so this is what it's going to be, right? We always have to be humble, because especially when we're extending inference from the average to the individual. All right, so let me give you an example here, and then someone is going to interpret. If you wanted to look at the difference in the average number of working hours of resident doctors in your community hospital, and somebody said there's a difference between, is there a difference? I want to ask, is there a difference between number of hours worked by females versus males? Okay. And when you coded this variable for gender, female was 1 and male was 0. Okay. How are you going to interpret the beta 1? Again, the female is 1, male is 0. How are you going to interpret the beta 1? How are you going to interpret the beta 0? Anyone?
Hello, sir.
Yes, please go ahead.
The beta naught.
Okay.
Is the beta naught is when it's a male.
When it's a male. Why is that?
That means it's since it's a binary variable that the males is 1 and the female is 0.
No, the male is 0.
So the male is 0 and the female is 1.
Excellent.
So that means is when beta 1x is 0.
Is 0. Excellent. Excellent. When beta 1x is 0, then, that which is in the context of males, right? Then that's what you would get for the beta 0. Okay, somebody else wants to tell us for beta 1. Thank you. Noah, you want to go? Badru Lawal, you want to go? Anyone else? Anyone wants to go, whether you've spoken today or not? What is beta 1? We just were told that the beta 0 is, the average for males, right? And so what is beta 0? What is beta 1? Anyone wants to try? It's right there on the screen, by the way. We're going to wait until somebody speaks up. Okay.
The one in this, since we are using a binary variable, if our x is female,
Yeah.
then we cannot equal to male.
So what's beta 1? Beta 1, not beta naught.
Beta 1 is the representation for the x, which is the one we coded with 1.
Is the what? Can you say that again?
What we coded for 1,
Yeah.
which is female in this example,
Yeah.
if it is now female, it's beta 1.
Okay, so don't go yet. Is it the increase in, or the difference between males and females, or is it the value for female? Which one is it?
Value for female.
Okay, so that's not exactly correct. So beta 1 is the difference between the female and the male. All right. So as you go from the 0 to the 1, that means that as you go from male to female, beta 1 is the change or the difference between the average. So say the working hours in male is 70 hours. The beta 1 would be something like maybe 2 hours, in which case the average in females will be 70 plus 2. Okay, let me say that again. If the beta 0 is 70 hours, and we said that is the average in the reference group, or the average in the group for which is, the 0, right? The 0 group, the reference group. Beta 1 is the difference between the reference group and the other group, which is the female group, right? The group you're interested in. So as you go from male to female, the difference between the number of working hours on average is that beta 1. So if beta 0 here is 70, beta 1 might be 2, okay? But if somebody asks you, what is the average working hours in female, it will be 70 plus 2. It's not the 2 that is the working hours in the female, it is 70 plus 2. And I think I might have an example here. Right, so this is an example. In this case, you have the average working hours in the male is 74. If you look to lower here, this table at the end, the beta 1 is minus 6.6. Okay, the beta 1 is minus 6.6. So obviously, we're not looking at a situation where females are working -6 hours, right? But what's really happening is that you add 74 plus minus 6.6, that will give you the average working hours in the female. So which in this case comes to like, 68 or something like that. Okay, so let me take that again. The beta 0 is the average. the beta 0 is the average in the male, is the average in the reference group. Okay. The beta 1 is the difference between the group that is the reference group and the group that you care about right now, right? Which is the category that you're talking about. Okay, so that is the beta 1. So if you're interested in the average for the female, you add them together. Okay, all right. So that's the binary. Is that clear, or do we still have questions? Is it clear, or do we have questions? Yeah, it's clear. All right. So what if it's a categorical variable? What if it's a categorical variable? So in the last few minutes, we're talking about males and females. What if we're talking about BMI? Okay. And maybe hours work. Let's assume, for instance, that, you know, obese people are working different number of hours from normal weight, from underweight, and your reference group is normal weight. Okay. Your reference group is normal weight. If somebody gives you a beta estimate for the obese group, how would you interpret that beta estimate? Anyone wants to give it a shot?
Sorry, come again with the question.
Okay. You're interested in how the number of hours worked differs by BMI category. Okay. And so for BMI category, you have underweight, normal weight, and overweight. And your reference group is normal weight. Okay. And your reference group is normal weight. For simplicity, I'm using 3 categories. If you're interested in the beta estimate, so maybe beta 1 for obese, right, compared to normal weight, how would you interpret it? First of all, what would be the beta 0? Normal weight is a reference group. What would be the beta 0? Anyone? Yes, go ahead.
I think the beta 0 will be the BMI for the normal weight.
Yes, yes. The beta 0 will be the BMI for the normal weight. What will be the beta estimate for the obese group? Anyone? Anyone? What's the beta estimate for the obese group? Yes, excellent. The beta estimate for the obese group will be the difference between the average working hours in the obese group compared to the average working hours in the normal weight group, because the normal weight group is the reference. Okay, so it's important to understand like how we interpret the regression output to be able to make sense of it. So that means that if you have a categorical variable that has 3 categories, normal, overweight, and obese, sorry, normal, underweight, and obese, or underweight, normal, and obese, and normal is the reference group, you will have beta 0, which will be the working hours in the reference group, which is the normal weight, but you will have beta 1, which is the working hours in the obese group, but you will also have beta 2, which is the working hours in the underweight group. And when you compare the beta estimates for each level of the category, you'll be comparing it to the reference category. So that means that you will compare normal weights, you will compare obese group to the normal group, right? You will also compare the underweight group to the normal group. So that's how we think about, that's how we interpret the regression output for the categorical variable. All right. And the same thing occurs for indicator variables. Remember, we said that indicator variables are really categorical variables, but we are presenting it in a way that each one is a separate variable by itself. Okay, so I won't spend too much time on that. The other one that I wanted to spend time on a bit is the multiple or multivariable regression, where you have more than one variable in the model. Okay, when you have more than one variable in the model, the beta 0 is the average working hours. So let's take an example where beta 1 refers to maybe gender, male and female, and beta 2 refers to maybe seniority, senior resident versus junior resident. Okay, and we want to look at working hours. The beta 0 refers to the average working hours of the individual when beta 1x is 0, right? And beta 2z is 0. We're essentially setting everything else to 0. Now, if the beta 1x is 0, that means that maybe the person is male, right? In the example that we've talked about where female is 1. In the example of the senior resident is 1, junior resident is 0. So that means that the individual that the beta 0 refers to will be a junior resident. So that means what we're really thinking about for beta 0 is a male junior resident on average. Let me take that again. When you have more than one variable, this is multivariable regression or multiple regression, right? When you have more than one variable, the average that you're interested in for beta 0 is the average when you set everything else to 0. When you set the first variable to 0, we said female as the example, where female is 1, male is 0, right? That it means that the person that you're talking about here on average is male. For senior residents, we said senior resident is 1, junior resident is 0. The person we're talking about here on average is a junior resident. So it means that the beta 0 refers to a junior resident who is male, a male junior resident. Is that clear? So let me ask you a question and then let's have somebody else try. If we're interested in working hours, okay, we're interested in working hours for a married person who has a child, okay? So the one variable, X variable, is married, yes or no. If the person is married, then the X is 1. If the person is not married, X is 0. The Z variable is whether they have a child or not. If the person has a child, Z is 1. If the person does not have a child, Z is 0. Okay, let me take that again. If the person is married, X is 1. If the person is not married, X is 0. If the person has a child, Z is 1. If the person does not have a child, Z is 0. And you're interested in the average working hours, and they're all resident doctors. How would you interpret beta 0? Somebody want to try?
Hello, sir.
Yes, go ahead.
I think the beta 0 is the average number of hours worked when the person is not married and does not have a child.
Yes, excellent. Person is not married and does not have a child. That is B0. The next question you want to understand is, what is B1? What is B1, right? We said B1, somebody want to try? We said X is for someone who is married, whether they're married or not married. Let's have somebody else try. Anyone?
Can I try, sir?
Yes, please go ahead.
I think B1 is the constant for married females.
For
Or let me say
married,
just for married. You said X is when the patient when the resident is married is 1, and when he's not married is 0.
0, yes.
So
Is the
beta
number
1
of
will
hour
be
is the average number of hours for
married.
Is it the average number of hours or what is it?
It will be it is the multiple.
The difference.
For the married. Okay, the difference for the married.
Yeah, the difference for the married compared to
the the single.
Compared to the unmarried person. Very good.
Married,
okay.
Yes.
But the other thing you have to say, because you have the Z in the model, what do you have to say? Don't go yet.
Okay. In which the resident is married but not with kids.
No, that's not. But you have to say that you're what? Adjusting for.
Adjusting for kids.
Yes, adjusting for whether they have kids or not.
Kids or not. Okay.
Okay. There is a situation where you can do all the adding and you can do all the adding, but that's in the prediction setting. Okay. So let's focus on this setting where, we're just thinking about the one particular variable of interest. This is the causal setting, right? So adjusting for whether they have a child or not. Somebody else wants to try for beta 2. If the beta 2 is what we were interested in, and you saw this model, what would you say? Go ahead. Yep.
Okay. Beta 2 is the contribution of whether the contribution of the average number of hours worked, which results to the increment in the number average number of hours worked. When a person has a child, adjusting for covariate X.
Yes, adjusting for covariate X. So the increase or the difference, right, in the average number of hours worked when a person has a child compared to if they didn't have the child, adjusting for whether they are married or not. This is the way to think about it, okay? This is the way to think about the interpretation. I spent some time on interpretation because if you understand how to interpret the linear regression, then you'll be able to interpret all the others too. All right, so I'll skip this. We already looked at this, and then we looked at other variables, other regression methods. And basically, once you understand everything that we just talked about, you just need to make slight changes in the what's it called that you talk about in the in the way that you present your interpretation. So for instance, if it's a logistic regression, instead of saying the difference, right, you will say the odds. So the odds of the variable is higher by, because now you're talking about in the context of multiples. In Poisson regression, now you're thinking about the mean, right? And here as well, we're thinking about you have to exponentiate, so you're also talking about in multiples. And the same thing in rate and the same thing in the Cox proportional hazards model. But once you understand all that we just went through in the first set, it'll be easy to translate that into this setting. And we went through this in the previous class as well. Okay. All right. So I'm going to skip this so that I can have a little time to talk about survival analysis